All right. Well, let's take a look at some higher order Airys stress functions and see what kind of stress fields we get out of that. So let's take one. F is equal to A4 xy cubed. Now, if I want sigma x, that's the second partial of f with respect to y twice. Okay, the first one would be 3a4xy squared. The second partial would be 6a4 x y. Okay, so that's kind of interesting now. We have a stress in the x direction that depends on both x and y. If I wanted sigma y, that would be the second partial of f with respect to x twice. Okay, that's 0. And if I want tau xy, that's the negative of the mixed partial second partial derivative of f with respect to x and with respect to y. And in this case, that would be equal to minus 3a4 y squared. So we get some sort of parabolic stress distribution. Well, what region do we have and how do we interpret that? Okay, well, one of the first things we tried was a rectangular region last time with plus and minus c surfaces. There's the x-axis, the y-axis comes up from here. So this would be plus c and this would be minus c. Well, let's sketch out what the stress fields are on the end of this object. We can think of it like a beam if we want. All right. We need another dimension. We need a length of this region. So we'll call it that dimension L. And we can plot what the stress fields would look like. The easy one, I guess, may be the sigma x. When we get to x equal to L, sigma x varies linearly with y. And it goes positive and negative. So that looks like kind of a bending distribution. That would be 6a4 L times y. So here we're at x equal to L. When we're over here on x equal to 0, we don't get any stress. Okay, that is kind of interesting. As we get further and further down the length, we get more and more of this linear stress distribution. Well, if that's all we had, that looks a lot like a cantilevered beam. Of course, cantilevered beams also have some shear stresses in them, so we do need to evaluate what that looks like. Well, the shear stress looks like this equation, minus 3a4y squared. And that's a parabolic stress distribution. There's something funny about this parabola, though. It's a parabola where the shear stress goes to 0 at the middle. So if we were to plot this out, here's the plane that I'm plotting. It's a parabola, but it does something like this. It gets bigger on the outside edges. And it's all positive, or it goes to 0. It's either 0 or greater. And so the shear stress distribution looks something like this. I'm going to draw these arrows as if they're kind of coming down this way. Well, maybe I should draw them up. Indicate positive on that face. On the lateral surfaces, the top and bottom, we have a constant shear stress. The value of the shear stress would be equal to, well, I guess there's a minus sign here. So if I was looking at the magnitude, it would be pointing up. The minus sign points it down. So what I'm going to do is I'm going to draw the arrows. I'm going to leave the arrows as I have them here. And I'm going to put this as a minus 3a4y squared. And up on the top, it's going to be equal to a minus 3a4c squared. And down on the bottom, it's going to be a minus 3a4c squared. But to keep this in equilibrium, these will go in this direction. And that value doesn't depend on x. So everywhere in that beam has the same parabolic shear stress distribution. that looks something like that. Well, what problem have we solved? Well, I don't know. If we look at that, it has some features, like I said, for a cantilevered beam, where the stress builds up as we get over to the wall. So the right side, where x equal to L, would be where the wall would be located, but the shear stress distribution is all off. If you remember from elementary mechanics of materials, the typical shear stress distribution we would have for a cantilevered beam would be a beam with a load on the end. We draw it so we know what I'm talking about. Typical shear stress distribution for that would be parabolic, but it would be maximum at the centroid or center line of that beam, the neutral axis. It wouldn't be zero, it would be a maximum. Well, we can fix that, though, by using superposition. Okay, so let's use a new Airys stress function that starts out like this. A4xy cubed. But now we're going to add a term that looks like this, 3a4 c squared xy. And this represents a constant shear stress. What we get in that case, if we make the adjustments appropriately, what we have is a shear stress distribution that varies parabolically with a maximum at the center line, and we have gotten rid of the shearing stresses on the top and bottom surfaces. Yet at the same time, we've kept our bending stress distribution. Okay, so now this is a cantilevered beam. Well, the last thing we need to do with this is we really don't know what loads we're applying to the cantilevered beam unless we do a little bit more work. If we take and we integrate this stress distribution for tau xy over that area, then we'll get the equivalent force in the vertical direction. And more explicitly, we can take our thickness to be 1 and we can integrate over that. We can integrate from the top to the bottom, and then we'd have the 3a4. We'd have a c squared minus y squared dy dz, and we can find out how these coefficients that we have in here relate to our applied load P. We can even get even higher, we can even have higher order Airys stress functions. I'm going to write this down and then we'll talk about it. This gets a little bit intricate, and I will try to make sure I don't make any mistakes writing any of these terms down. You may want to refer to your book just to make sure. It's a c squared and a y cubed. And then a 10c cubed and an x squared. Believe it or not, del fourth f does equal to 0 in this case. You may want to verify that. The stress fields do look something like this. Sigma x is equal to 3 q being some kind of constant, times y over 4c cubed, x squared minus l squared, plus this other term qy over c cubed, 0.3 c squared minus 0.5 y squared, sigma y is going to look like q over 4c cubed, y cubed minus 3 y c squared minus 2c cubed, in tau xy will look like 3 qx over 4c cubed c squared minus y squared. Alright, well, what is that the solution to? Well, if we start with our rectangular region again, it kind of looks like a beam that is c on the top and c on the bottom. If we put our coordinate system at the middle of this region, we would find that we end up with a traction on the top surface that's equal to Q, which is a pressure, and that we have some distribution of stresses that represents a simply supported beam with a constant load distribution. Now the units on this Q would be something like force per length divided by the thickness, 1, unit thickness. Alright, so there's a lot of interesting things then that you can look at. I'll let you dig into this one in more detail. You can verify that I wrote down the stresses right from that potential function, that Airys stress function. You can verify that del fourth F does equal to 0 in this case. And then you can take a look at the edges, and I guess I need to make sure I write my definition of L. It's a beam of length 2L. You can see that the stresses on the surfaces vanish otherwise, other than the top where we have that traction Q. Alright, we'll give those a try, and there are many different types of Airys stress functions. In my opinion, one of the most interesting Airys stress functions comes about when we use complex variables to define our stress function. And in fact, that's what we can do for crack tip stress fields, looking at the Westergaard solution for the crack stress fields in a plate with a crack in it. And we can look at the singularity, the stresses that shoot up to infinity near the tip of that crack, and investigate the nature of that singularity. And we'll actually do that in one of the last lectures in this class.